And good morning. Can you hear me?
Morning.
Okay, thank you. Thank you for the response. Here is Dr. Tsai Lin from National Cheng University, and I also serve as the organizer of this online course. And the online course is a SAR remote sensing for environmental monitoring, start from today to the end of November. So before today's course, we have a show opening for this online course around 15 minutes. Introduce this online course. So here in this online course, we will use the Google Meet. I'm not sure should be most of the audience familiar with this platform. And can you send a short message on the chat room at the right button? Can you show everyone can send a short message to make sure you are okay for this platform? They have the chat room in the Google Meet. Okay, thank you. Right, that one. So during the course, you can, in case you don't like to show up, you don't like to turn on your webcam, then you have a problem to the any kind of suggestions, even questions, you can use the chat room to post your questions, including the opening here. Okay, this online course is hosted by TSU, it's a Taiwan Space Union. Then this is the Union of Space Science and Space Engineering, especially in Taiwan. And it was initiated by Professor Ye. He is a senior professor, senior and famous professor, not only in Taiwan, but also in the world. So you can find the goals here. The goals this union to promote space science and technology, to promote development in space, commercialize and industrialization, and to promote international cooperation. So this online course is based on the third goal, promote international cooperation. Okay, so this is the speaker in this online course. I will not to introduce one by one. You will meet them in the courses. Here is the topics including in this course. They can separate to 3 parts. The first part is introduction to SAR. It's also today's topic. And you will to learn the best concept, the fundamental knowledge of SAR, and also their applications. Is the speaker is the Professor Chang. Then the second block is some of the topic related to SAR data processing, and also contain a hands-on experience by using the snack. So it's quite good to have you can when you move to the application of SAR, it's better to see the data, the characteristic of the data. Then the third block is applications. You can regard it might talk high-level application of SAR, including Crustal deformation, flood detection, surface deformation, and sea level rise, the land subsidence, that kind of applications. So in case that you already have the fundamental knowledge of the SAR, you can move directly to the block application of the SAR. In case that you are the beginner of the SAR, then I would suggest you to take the courses here including the introduction to SAR data preprocessing, then it will be helpful for you to understand the application in the talk over here. The end of this online course have the presentation and a short quiz. It's not an exam, it's a short, simple and short quiz. Then in the presentation, we will invite some of you to share with your study, even if it's only the best concept. It's still worth to share the concept with us. We have the group in the Facebook, and we invite all of you to join in this group, and we will announce some of the information about this short course over there, such as maybe we will postpone a little bit, maybe 30 minutes, maybe 1 hour. Then we announce that kind of information over there, because there you can receive the information immediately. We can to share with some information, yes, we also can meet the people, members in this course over there. So already you can use the QR code. Maybe it will be easier to, we have posted the link on the chat board. You can use the link to join in this group. Maybe I can wait here for you to join in. Here is the, okay, here. Now it's 30 members. So this is the group here. Then now we already here is the teacher assistant Mengzi. He posts the information of today's lecture here, also the link, and also here you can introduce yourself shortly. Here, where you come from, where's your institute or university, what is your study, shortly introduce yourself here. Okay, please join this group. And another thing I would like to deliver is as I mentioned, one of the purpose is the international cooperation in addition to the interesting SAR courses. So the social networking is also important here. Especially in this online course, we only can meet you online, and it will be somehow difficult to interaction in between the members. So I will arrange 2 events. It's a social networking event in next 2 weeks before the courses. And in this event, I will invite some of you to provide a short introduction around 3 minutes. It can be the one. It's better to prepare PPT slides, maybe 1 or 2 PPT slides. Here I select some members here without inform you. I select it from the Facebook the group. So in case that okay for you, you can let me know on the chat board. Oh, it's somehow you don't want to somehow to prepare this introduction. You have no where also let me know that. And here I show you a short demonstration how to prepare this short introduction. Okay, it's an example. Here, it's not difficult to recognize me. It's the only professor in the campus in the NCKU with the thin hair. So I always wear her hat in the campus. And my name is Chih-Heng Lu, is a professor in Department of Geomatics, National Tseng University. It's located in Sangsen, Taiwan. And my lab is a AI lab, geospatial artificial intelligence. And my research includes geospatial deep learning, satellite image processing, information visualization. Also, I would like to introduce a little bit my university, National Tseng University. It's located in Tainan over here, around 4 hours driving distance from Taipei. It was the capital of Taiwan in 1961. When national hero Kuo-Hsin Tseng recovered Taiwan from Dutch. So the name National Tseng University, named after this national hero Tseng. It's a comprehensive university, 9 colleges, 43 departments, and more than 20,000 students. Also, it have the modern buildings, big campus, like Lake One. Here's the building of the geomatics. And located in here, the main campus located in center Tainan. We also have another 3 campuses around the Tainan. And so it's a simple demonstration to introduce yourself. I don't know I select some of people here. Erwin Molina. In case that are fine for you to provide the introduction the next week. You can send a short message in the chat room to let me know that. Then the second one is Harvey Hachiro, Australia. I don't know, is you online? And then the third one is Argon, I don't know how to pronounce it. And the next one is Paul Giuliano. And the last one is Wan Ming. Okay, anyway, we have the lecture. Then Monza will contact with you for this short introduction the next week. And it's a time to move to the first course. Then the speaker of this course is Professor Zhang Zhongbai. The photo here is took several years ago, and now it's more handsome, more mature than the photo you see. And you know that to be the first speaker in the sequence of the courses, I mean, in general, is a big guy, big guy in this sphere. And now is a professor in National Central University Center for Space and Remote Sensing Research. And also here is his the research, structural geology, geological data processing, and also remote sensing, geological remote sensing. And so Professor, now the audience, the floor is yours, the stage is yours.
Okay, thank you, Professor Lin. Thank you so much for your kind introduction. Thanks again to Professor Lin. Before engaging today's topic, I want to share. Firstly, I want to show this photo to you. I think the principle of remote sensing is quite simple. It's just like we can use the photo took by satellite, and then we can, for example, a hazard event or some event, and then we can compare the image, the photo acquired took before the event and after event, and we can compare these two photo and or several photo and try to find the change on the lens surface. These two photo just acquired before a typhoon event, and then the other one, the left hand side, right hand side is after a typhoon event in southern Taiwan. It's a typhoon event in 2009. It's a Morocco typhoon. You can see a very huge landslide occurred during the typhoon event and totally destroyed a village named the Shaolin village. So by using we can say the optical photo, the optical remote sensing, you can do this kind of research, or we can say this kind of application directly. And I think most of you have already the basic knowledge. Okay, so to do more research, to do some more how to say attract more information. For example, I will show you next one. We use different the image of different acquired by different sensor with different resolution, and also we use the 3D model and to compare the event before and after. Left hand side is before and right hand side is after. You can see the houses and right now are all covered by the debris flow, and we can also this kind of application is quite useful for the hazard. We cannot say mitigation, but for the first help for this area, for the hazard area. But problem is that for the optical remote sensing, actually you can apply for the lens surface change detection, but for the slight and largely distributed deformation, for example, the deformation associated with the earthquake or the lens subsidence caused by water pumping, actually is almost, but still possible, but it's very difficult to be detected or to be recognized by using by comparing the optical image directly. So today we are talking about a technique. Actually, it's not a very new technique. It's since around 30 years we how to say we well developed this technique, and it's already applied for many cases. So today I will talk you about this case, this technique. We call it a radar synthetic aperture radar system. We call it a SAR, but it's principally acquired by satellite. So it's a spaceborne radar. So today I'll talk you about how to apply the radar technique, especially spaceborne. Okay. So right now there are many satellites. We have installed the payload, the radar payload on different satellites. Here is a very simple list for this satellite. You can see the first one is a CSAT. Okay, it's launched in 1978, and then the satellite, the radar satellite, launched by Canada and the European Space Agency, and so on. There are a lot of satellites right now, more than 10, I think. So here is the list of the name of these satellites, and I'll show you some new satellites here. Sorry, right now there's an earthquake right now in Taiwan, so we have the lecture by in the shaking of the earthquake. So these three are most new satellites, including the AROS-2 launched by JAXA. It's a Japanese Space Agency, and Sentinel-1 and 1A and 1B launched by by European Space Agency, and also satellites launched by NASA. You can check the payload capacity of the payload and the characteristic of the payload by yourself. On the internet, there are some many websites. There are some many detailed introduction. So it's this one is a Sentinel-1 and B. Actually, I show you this one because this one is you can download for free. So many researchers prefer to use these satellites. Yeah. Okay. And it's a orbit coverage area of this satellite, the Sentinel-1, and there's, of course, this satellite, this radar sensor has the radar sensor of Sentinel-1 has a different mode. Normally, we use the first one, the interferometric wide swath for our interferometric analysis. Later, I will talk you about what is interferometric analysis. So, if you want to more details, or you want to submit a project to European Space Agency to obtain more images, you can contact this website and send your proposal to there, and then you can have a quota of high-resolution satellites. For example, the let me see, SAR and so on. It's also for free once your proposal be accepted. Okay. So if you want to know more detail and more principle and application cases, you can read this. You can visit this website. Okay. So right now I will talk you. Let's come back to the SAR application. So here is a very brief history of the spaceborne radar. The idea of imaging the Earth's surface by radar, by radar sensor, actually is arose in 1950s after the Second World War. And the first satellite, as you know already, been launched, that is CSAT, been launched in 1978. But unfortunately, this satellite kept in the orbit only for several months, so we don't have many images from these satellites. And then the EIS-1 actually is launched by the European Space Agency to open the new epoch of the radar application. It's launched in 1992. And this one kept in the orbit for very, very long time, more than 10 years. And then in 1 or 2 years later, the EIS-2 has been launched, and then by the tandem model, they acquired a series of radar images covered all the globally covered. So during this period, we will develop many different techniques by using the radar image acquired by these satellites, and then successfully observe the many cases. Later, I will show you several. And the first publication by using the two radar image pairs and to observe the deformation of the earthquake is published in 1993 by Massonet and so on. They published this result in Nature. Later, I will show you this result. And then when I studied in France, I learned this technique. Actually, Massonet is French people, so I learned the technique after them, and then we start to apply this technique in Taiwan, and we the first paper published in 2001 concerning the deformation in southern Taiwan. And then because still the interferometry technique still have some limitations, so last 20 years we developed many new techniques to overcome the limitation of the InSAR technique. Later, I will talk about it all that. So this is the topics that I will present today from the radar. What is radar? And then the radar actually is not for generating the image. So we have to do some improvement to, how to say, to generate a high resolution images. And this technique, we call it as a synthetic aperture radar. And then by using the radar image with a high resolution, actually we can try to generate, we can use that image pair to generate the DEM, just like a stereo optic image pair. We can use two optical image and then looking from different angle with different looking angle, and then we can generate the DEM. This is the same technique. We call it as an interferometric. It's not a stereo. It's just use the phase difference to generate that. So we call it InSAR, interferometric SAR. And then we can use this technique to see the surface deformation. This technique is a differential InSAR. Okay. And last topic is a, how to say, advanced technique of the InSAR. We call it a persistent scatter InSAR. Actually, for the advanced, so-called advanced InSAR, right now there's many new technique, and the PS InSAR is only the one technique that well developed and widely applied. And also there are some, for example, small baseline, blah blah blah. I don't have time to talk to present you all these techniques. So if you are interested, maybe later you can check it by yourself from the internet, or you can, maybe some other professors in their lectures will talk about that. So I will stop today's lecture on the PS InSAR. So all these 5 topics, how to say, after all these 5 topics, I think you will have a general idea, general knowledge about the radar and SAR application. Okay, so let's start from the first topic, the radar. So what's the radar? Radar actually is a detecting, how to say, we use the radio wave. We use the radio wave to detect and range the object. So it's an abbreviation of the radio detection and ranging. Okay, we use the radio wave. Actually, radio wave is much longer than the visible light. Later, I will show you the spectrum range. And then this cartoon you can see. On the left is a sensor. Sender actually is also a receiver. The sender launched the radio signal. Is shown by the red curve and touch the object, and then the object reflect the signal shown by the green dashed line and received by the receiver. So if the object is far away, the receiver, and how to say, the receive time will be, the interval time will be longer. If it's approaching, and the time will be shorter. And if the object is larger, and the signal, the receiving signal, will be stronger. And if the object is smaller, and the receiving signal will be weaker. So by using this principle, actually you can detect, you can range the object. Okay, so the radar firstly is how to say, developed for the military use. So the object normally is the aircraft or the ship. Okay. So this is a microwave spectrum, or we can say the radio wave spectrum. Normally, it's the wavelength is between 1 centimeter to 100 centimeter. or we can say 1 meter. So it's 1 centimeter to 1 meter. Okay, but for the wavelengths, long wavelengths, it has the stronger penetration capability. And for the shorter wavelengths, the microwave with the shorter wavelengths, and the capability of penetration is lower, but it's more precise. We can have a more precise information. So it depends on your purpose, what kind of object you want to detect. You can choose a different the radio of different wavelengths. But normally for the geodetic purpose, because we use the radar satellite, generally we use for measuring the surface deformation. So for the geodetic purpose, we use normally the wavelengths ranging from 2 to 30 centimeters. So for the 2 is a 2 centimeter is a C band, X band between the X band to C band. X band is 2.5, 2.4, and to the C band is 3, blah, blah, something like that, to 5 centimeters, 7 centimeters. And for the arrow band, it's normally 50 to 30 centimeters. So we use X band, C band, sometimes S band, but not frequently. But we use many arrow band for the satellite payload. So normally from 2 to 30 centimeters. So here there are some frequency range used for satellite or aircraft. So you can see K band and KU band. This is too short for the remote sensing, for the geodetic purpose, and the penetration capability is too low. So normally we don't use that. P band is too long, so it's not the result is not precise enough. So we use normally X band to arrow band, including the SRTN. It's a space shuttle mission, and the radar satellite, radar set, MV-SAT, that is C band, and this JERS, ALOS, these are Japanese satellites. Most are arrow band because they want to see more. They want to see how to say the tropical and the subtropical area with dense vegetation, and in the mountainous area, so they choose the arrow band with a larger looking angle. So that we will talk about later. So, but as you know, as I mentioned before, that the radar, the first is developed or how to say designed for the military purpose. So they want to detect the aircraft, for example. So the aircraft, actually, if you want to avoid the detection, the best way is to try to fly as close to the land or sea surface as close as possible. So by this way, let's come back to this one. You will see that the return signal will come back with the return signal of the object will come back with the land or sea surface altogether, if the object is very close to the land or sea surface. So it's very difficult to be separate, to be distinguished. So this is the best way to avoid the detection. So you can see at that epoch, the signal from the land surface actually is a noise. Only the signal from the object is information. But after the Second World War, of course, we developed a lot of many radar systems. So what you can use, what you can apply by using these radars. So some researchers think that maybe we can use that to generate an image of the land surface. We can use this before, that is noise. but right now we can use this noise to generate, to attract some information. And the idea is very simple. The technique, we call it as a SAR. We just launch the radar signal. We put firstly the radar system on the aircraft and launch the satellite, launch the radar signal only to one direction. We call it the side-looking airborne radar. Just like the figure A, you can see the aircraft here and launch the signal, the radar signal to only one direction. And you can see for this direction, the house is closer to the aircraft and the tree is farther than the aircraft. So here, the house side, we can say that is near range, and to the tree and the this area, we call it as a far range. And for the near range, the return signal will come back to the sensor, to the receiver earlier than the far range. So we can see the house here, and this is time, okay? And because the wall of the house is generally perpendicular, it's generally vertical, so it's perpendicular to the land surface, so it's a perfect corner reflector. So you can see the signal touch the land surface and come back by the reflection of the wall of the house. So the return signal will be very, very strong because it's perfect corner reflector. And this signal come back to the aircraft earlier than the reflect of the tree. For the tree, of course, the tree trunk is also vertical to the land surface, but it's much smaller than the wall of the house. So the return signal and the tree top, actually, the leaf is not so perfect reflectors. So you can see the return from the tree is not very beautiful, but still you can see the return from the tree. So, but later than this one. So this is a scan of the side-looking airborne radar. And if you scan one line by one line along with the track of the aircraft, and then we combine all these return signal, and we can generate an image. So we call this kind of image of side-looking airborne radar image. So it's just after Second World War, we start to develop this technique. And of course, the return signal, actually you have only the, how to say, the amplitude and the timing from the profile. So by using the timing, you can put the location of this object, and then the nature of the object, actually you can use the amplitude of the radar image to recognize that. I show you some cases here. For the very flat surface, for example, the airport or water surface, actually that is a perfect, how to say, you can just consider that a mirror. So it's a perfect reflector, but reflects to other direction. So this area, normally you can see in the image is black. For the forest, there are so many tree trunk and tree top, and you can see the dot pattern here. For the cropland, for example, rice field, you can see the boundary of different field. So just like this one, and we go to the last one for the city, for the city area, or for the rural area, there are buildings. As I mentioned before, the buildings, the perfect corner reflector, so we can see the geometry like this one. Okay, the block shows the building. And for the mountain, for the mountainous area, that's more interesting. You can see for for the mountain, because you will have a slope fast to the satellite, fast to the radar. Another slope is how to say, you will have a shadow of the radar sensor. So you will have a symmetry pattern, and for the shorter slope, actually you have a stronger reflection signal. The amplitude is larger, and for the longer slope, it's in the shadow side, so it's darker and it's longer. The reason I will show you here. You can see the figure B. A, B, C shown here is a symmetric mountain. The distance between A, B, and B, C is the same. And this is a sensor. It's a radar sensor. Okay, so you can see the radar launched the sensor launched the signal and touched A and come back to the timeline, the image plane at the A prime, and then touch the B, come back at time of B prime, and launch to the C and receive at the C prime. You can see the distance between AB and BC the same, but along the image plane, actually along the for the receiving time, the A prime B prime is much shorter than B C prime. And because we generated the satellite image by using the receiving time, of the radar signal, so we will generate an image of the mountain, but with a shorter slope here and a longer slope here. And normally for the shorter slope, that is fast to the sensor, and we'll have a stronger retinal signal, and BB prime for this slope. Of course, maybe sometimes there are some shadow, but normally, if even you can receive the signal from this side, and the altitude, you can the amplitude. The amplitude is much weaker than this slope. Okay, so we can use just this this data, this kind of retinal signal to generate a radar image. I will show you an example. Before showing you the example, I will talk to you about another technique to improve the image resolution. For the radar, normally radar image, the resolution depends on the size of the radar panel. Okay, if the panel is larger, and the resolution will be higher, just like the optical sensor. If the diameter of the object of the lens is larger, and then you can acquire the resolution of a higher resolution image of a higher resolution. But it's very difficult to launch satellite with a very large antenna, radar antenna. So the resolution, the normal resolution of the radar image is very low. And for the image acquired direct by one radar image, okay, or we can say by only one time, and then the resolution normally very low. We call it the real aperture radar. The real aperture means the real size of the radar panel. Okay. It's a little difficult to say. Normally, I give you an example. For example, you launch a radar, your satellite with a radar panel of 10 meters. Actually, 10 meters of radar panel is quite large, okay? And then in the orbit of 1,000 kilometer high, and then you can generate by using the real actual radar. You can obtain a image of a resolution of 10 kilometers. Okay, 10 meters of radar in the orbit is 1,000 kilometers high, and then normally the radar images with you can have only the 10 kilometers resolution of the radar images. It's too low. Normally, it's too low for the remote sensing application. So we have two. One question is that we cannot use that directly. We cannot use the real actual radar to do the to generate the image and for the remote sensing application. So we have to. The first challenge, the first task is that we have to improve the radar resolution. The idea is that we can use several images, a series image, and combine all these images together. And of course, here there are some technique we call it focusing. We're using the Doppler effect to try to find the location of the same location, because in the radar image it's very difficult to find the pixel with the same location. But we can use the Doppler effect to find that. I don't want to talk too much detail. The general idea is that we use a series image, and then all these image along the track, a satellite moving track, and try to find the same location, and after combining into all these series of image, we can largely improve the resolution of the radar image. This kind of technique we call it a synthetic aperture radar. The aperture means the size of the radar. Okay, so this one is the real size. Okay, real size radar, and here synthetic means that we generate a huge size of radar, but actually it's synthetic. It's not a real. And for example, as the example that I mentioned before, 10 meters of radar in the orbit of 100 meters high, and you have an image of 10 kilometers of resolution. But if you use we acquire the image with 1,000 hertz, means that we acquire the 1,000 image in 1 second, and then combine all these images together, we can improve the image 1,000 times. And then the 100 kilometers resolution image will be enhanced to 10 meters resolution. The general idea is that, but the real situation, the real situation is much more complicated than that. But you know that actually it's acquired along with the track, will acquire the series image and focusing the image to improve the resolution. And this is an example of the Ukraine, in the southern Ukraine, Crimea Peninsula. And this is a real, left-hand side is a real aperture radar, the RAR result. And left-hand side is a synthetic aperture radar, the SAR result. We improve the satellite image to the right-hand side. We can see much the detail of the sea surface and the land surface. There are coupland on the land surface. It's very, very clear. So by using this technique, I mean SAR, is already ready for further application. So we cannot use the radar directly. We have to use the SLAR to generate the image, and then we use the synthetic aperture technique to improve the resolution. And right now it's ready for further application. Oh wait a minute. So this is just a case around 20 years ago. We acquired the image of the northern Taiwan by using the MVSat satellite. So in this image, you can see the two black bar here. That is airport, because that's a perfect flat surface. So all signal be reflected to the other direction. And you can see the mountainous area. All this is the northern part of the central range of Taiwan. You can see the mountain, actually, they are all asymmetric. Actually, the mountain is asymmetric, but here are all asymmetric. And then you can see the slope face toward the north, toward the east is shorter, but it's lighter because the satellite right now on the east of Taiwan and they launched the signal from east to the west. So the slope face to the east, toward the east, will have a stronger stronger return signal, but because as the geometry I mentioned before, so the slope will be shorter and shorter. And the other side, you can see face to the west, okay, it's longer, but it's darker. So, and then for the metropolitan area, for example, in the basin here, it's a Taipei Basin. You can see the building here, and the Taoyuan city here, and the Zhongli city, we are now here. You can see the lighter spot, they are the building. So, because the satellite normally is it's a side-looking radar. So for the most satellites, the default situation is right side looking. Means that the satellite look always on the right-hand side. So the satellite is right now on the east of Taiwan, at the east of Taiwan. So it's a right side looking, so it's a moving from the north to the south, and the look from to the right hand side. So it's a descending mode and acquire this image from the east of Taiwan. Okay, you can see also the river here, okay, and the sea surface here, and some wave, but still it's darker. Okay. So it's a very general idea of the SAR, or we can say the satellite SAR images. You can use that already use that for many applications. For example, I show you firstly. Before that, we see the satellite. It's a EIS-2. I took this photo in Toulouse, in France. Okay, and the MVSat satellite. We can use this satellite, this image for many applications. For example, this is case before and after a typhoon event. Before, this is after a typhoon, the Udor is in 2001. After this typhoon, a debris flow, we can say landslide, blocked this river, and there is a natural dam, and this natural dam blocked the river to generate a barrier lake. So this is a temporal lake after this typhoon event. Okay, so we took this photo at this time, so we can see the black area is a lake. But 1 week later, another typhoon attracted this area, and because of the very huge precipitation, and the water destroyed the natural dam, and the lake disappeared just after the typhoon event, because the natural dam, the barrier is disappeared. Okay, so you can see even during the very bad weather condition, you can see directly the change of the water body. Okay, and of course it's very useful for the inundation, for the flood event detection. This is around 10 years ago in the southern Taiwan. This area, the Pingtung area, was flooded after the typhoon event. The blue area shows the flooded area. You can see we compare the image before typhoon event and after typhoon event. The sea surface is a perfect flat area, so it's normally it's black. So you can see the black area over here. In this one, there's no this black area. And just after typhoon event, 1 week later, after typhoon event, we can see that. So it's a flooded area. So it's a quite easy to be applied to detect it. If you use optical image, it's not so easy to detect. Even you can have a very clear images still sometimes by using the color, the color of the surface. It's not easy to find the water area and the land surface to distinguish that. And the other thing is that during the typhoon event, normally the weather condition is very bad, and this area normally is covered by the cloud. And I will show you another case. Wait, before that, let's see the earthquake, tsunami. It's around 10 years ago in tsunami in Japan. You can see also the blue color shows the inundation, the flood area caused by the tsunami. Okay, you can see some more details of that. And also we can use that to distinguish the oil spill. Here you can see the black line here. We enlarge that this area, you can see the black line very clear. Actually, this is a ship. And then during the typhoon event, this is optical image of at the center of this area. You can see the Taiwan. This is Taiwan Island. Taiwan is covered by the typhoon. So if you use the optical satellite, you can see nothing. You can see just a typhoon image. But we use the radar image because the penetration capability of the radar is much better than the visible light. So it can penetrate the cloud, penetrate the smoke, and touch the sea or land surface and return the signal back to the satellite. So you can see on the sea surface, you can see this black line. It's during the typhoon event. All your boat, they put their dirty oil on the open sea. So this is a very bad thing, but normally it's very difficult to find that, and we use the radar image and can catch this event directly. So it's very, very useful. You don't need to have some spatial analysis. You just plot the image and you can see the details. And some other cases of the other case of the oil spill, you can see the black area actually is the oil spill. And for the land sea surface, because of the wave, so you can see still some dot on the sea surface. But for the oil, because the viscosity is much higher than the water, so you can see it's compared with the water, is a better reflector. So we can see very dark color on the oil surface. Okay. Then we can use also the radar image directly for example, military use. This is the image of always from Ukraine, from the Crimea Peninsula. In this harbor, you can see some. This is the radar image of this harbor. We enlarge this yellow rectangular frame, and you can see two boats. If we enlarge that again, you can see these two boats. And because the the satellite radar acquired the image by side-looking direction, so the radar signal will touch the water surface and reflect to the one side of the ship or the boat, and then reflect to the satellite. So you can see the profile. I mean the close profile of not close profile. Actually, the profile of the of the ships. So you can see. Normally, if you use the optical satellite image, is acquired from the top. So you can see only the top of the shift. But here, by using the side looking technique, you can see this one is a Kara class, and this one is a alligator class. Okay, so it's very useful for the military case. So, and then I will talk. This is for the case I present. I mentioned till now. It's a how to say? It's a very general use. You can use that directly. You don't need to do more the difficult analysis or calculation. And then I will talk to you about some advanced application. The first one is InSAR. We use a SAR image, but we use two SAR images and then to generate a digital surface model. This technique, we call it as interferometric SAR. So this is InSAR. So just the idea is very simple. Just like an optical image, if you acquire the two images from different looking angle, and then you look these two images directly, this image pair directly, and then you can calculate. You can have a how to say the stereo image, stereo image, and then you can generate a digital surface model. And radar, actually, we can use the same type, the same idea. We acquire an image of the same area, we generate an image pair of image pair of two different view angle. And here, this the baseline is very important, just like an optical technique. I will show you this one. I enlarge this one and show it here. For the optical images, you can have how to say, you can have the stereo view directly. But for the radar, actually, you don't have the stereo view, but you have the phase difference. Because as I mentioned before, the wavelength of the radar signal is much longer than the visible light. So you receive the image, not only the amplitude, but you receive. So for wavelength, for a C-band radar, for example, the wavelength is 5.6 centimeter. So for each 5.6 centimeter, it's a 2 pi. Okay, it's a 2 pi in phase. So for each pixel, you have the amplitude, and also you have the phase of the radio wave, the return signal. Okay, and then we can compare the phase of two images, and then to generate a digital elevation model or digital surface model. The idea is that we acquire the first image here, we call it the master track, and the second image is a slave track. And for there's a baseline between the master track and the slave track. But for this baseline, we can separate that into two components. The first one is a parallel component we call the parallel baseline. Okay, this one. And here is a perpendicular baseline. For the parallel baseline, it's not important. It's useless. Because if you acquire the first image here, for example, and second image here, actually, if you compare these two images, and then the phase difference between these two images will be a constant of all pixels. Only the perpendicular baseline, for example, from here and from here, actually, because the view angle is different. The view angle is different. So the perpendicular baseline is a important role. It's actually the crucial role to generate the digital surface model. And the perpendicular baseline can, how to say, actually can be calculated considered in this equation. So here you can see a constant and over a perpendicular baseline, and you will obtain a value we call it HA. The HA is the altitude of ambiguity. Okay, so the altitude of ambiguity is very important for InSAR. Actually, it is the value of each circle of fringe. What is the fringe? I will show you later. Okay, so means that if you have a larger perpendicular baseline, if you have a larger distance between the mass and the slab images, you will have a smaller, wait a minute. You will have a smaller HA. You will have a smaller amplitude of ambiguity. If you have a smaller baseline, and you will have a larger altitude of ambiguity. Okay. And I think I know this is a little difficult to understand, but this just to show you an idea. Okay, the real situation, the real case, actually you have to do many calculations, but I just simplify that and use only this equation to explain you that. We will come back to this figure later. I will show you a real case, and then you will understand what is altitude of ambiguity. This case is from this mountain. This mountain Etna in Sicily island of Italy. Okay, this volcano, this is an active volcano, and we have in the human's history we have more than 100 eruptions occurred here, and in 1992. Later I will show you another case from the deformation, but you know I just show you the topography of this mountain. Okay. We acquired the two images of this mountain, and then we generate this figure. This is topography of the mountain Etna. Okay, from the optical image to this one, in this image we use two radar image and then compare the phase difference of each pixel and generate this one. You can see the fringe. The fringe is an interferometric fringe of the mountain. Because of the view angle is different, so the topography can be revealed by the fringe in this figure. And what is the fringe? The fringe shows the phase difference and is caused by this one. We consider this as 10,000, okay? It's 9,000, but 10,000 is more easy to be calculated. So 10,000. If the baseline is 100, and then 10,000 over 100 equal to 100. So HA equal to 100 means that here the interval of each fringe equal to 100 meters high. So you can consider the fringes as the contour of topographic map, the topographic contour of this area. Okay, so the interval of each contour is controlled by HA. So if you have a larger baseline and the density of the contour will be the contour will be more dense. If this is smaller, and this will be less dense. If this baseline is larger, and then this will be smaller. If this is smaller, and this will be larger. If this is 100, and this will be 100 meters. Means that 100 meters between each contour. So right now you know that if you acquire the image of the same area of a the same area by using a different view angle from with a the baseline, the perpendicular baseline, and you can use directly these two images, each image pair, to generate a contour map just like this one, and the interval of the contour depends on the distance, the baseline. Okay, so we can generate the digital digital surface model directly by using two images. Okay, two radar images. Of course, the baseline is a crucial rule, very, very important rule for generating this digital model, surface model. So you can see that if this technique actually is very, very quick and we can say economic and very powerful. So, but for this for image with or we fix the baseline is difficult, and for the satellite, you know, every time it passes the same area, the orbit will be slightly changed, and you have to calculate the precise orbit and then to generate the digital surface model. So people says how to say, think that maybe we can use aircraft or satellites or of course space shuttle, and then we scan the surface at the same time, but by using the two sensors with a fixed baseline. So this idea actually has been carried out by this one, by space shuttle. We call it the shuttle radar topography mission, SRTM. The space shuttle has been launched. How to say, they use a bar of I don't remember. It's around 60 meters long. So there are radar sensor here and another one on the space shuttle. So they scan the surface at the same time with different wavelengths. It's an L band and C band at the same time. So very quickly, during only several missions, they acquired more than 80% of Earth's land surface. Okay, so they released the data by the United States USGS Geological Survey. You can download the data directly from the USGS United States Geological Survey website. That is for free. Before it released only the data of 90 meters resolution, but right now the 30 meters resolution is also launched for free. So you can download like this data directly. So this is the how to say, the most important data released by InSAR technique. And right now, of course, we can use the aircraft to scan the surface, approaching the land surface to scan by using different band and to obtain more detailed data. And of course, even after the typhoon event or during the very bad weather condition, the LiDAR cannot work. You can still use the SAR system to scan the surface to generate the digital surface model. This is very, very powerful technique. But in a special case, we come back to this one. If the baseline is 0, what we will see? The HA will be infinity, or if it's very small, the baseline is very small, and the HA will be very, very large. And then you can't see any topographic, or you cannot have any elevation data, elevation information from this image pair. So if the baseline is very, very small, actually the InSAR technique cannot be applied. So we prefer to have a larger, but too large is not good, but it's a larger, for example, 100, 200 meters of baseline for the InSAR technique. But come back to the idea, if this is very, very small, this will be very large. But if you still can see the fringe, and the fringe will be generated, or the fringe will represents not the topography, not the elevation, but the deformation. So we try to find a very small baseline data for the image pair for some spatial event. For example, land subsidence event or earthquake event. Let's compare to this one. Okay, so this technique, we call it as a InSAR, differential interferometric synthetic actuator. It's like this one. The left-hand side is a InSAR technique, you know already. But for this one, the satellite acquired the image of this area always at the same position, or with the orbit very, very small. The first one and the second one, and during the first one and second one, there is an event, the earthquake event. So if you compare these two images with very small baseline, but you can still see the beautiful fringe, that a clear fringe that are caused by the Earth surface deformation. I still use this mountain Etna case to explain you. Of course, again, the real situation is much more complicated. This is just a simple idea, simple cartoon. And for the mountain Etna, you know that it's volcano. So that's very active. But as I mentioned, during the human history, we observed more than 100 eruption events. Even in 1993 and 2003, there were two very big eruption events. And I give you this example is in 1993. Okay, just after the ERS-1 been launched. The ERS-1 has been launched in 1992. And in the 1993, eruption occurred here. Okay, so I used two images. One before, one just after, one is after 1 year after the eruption. You know, if the volcano just after the eruption of the volcano, because it's still very hot, so the magma still under the volcano, so the volcano is higher. And 1 year after the eruption, 1 year later, the volcano will be cooled down and the magma will migrate to other place, to lower place. So the volcano normally slightly subsided. So just like this cartoon, you can see the red line shows the topography just after the eruption. It's 1993 of the mountain Etna. And then 1 year later, the volcano cooled down and the topography is shown by this blue line. Okay, and the satellite passed this area just after the eruption and acquired the image of this area. So just like the wave, the red wave, and touch the surface of the volcano and come back to the radar, touch the volcano and back to the radar, and touch the top of the volcano and come back. Okay. 1 year later, the satellite passed through the same area, But you may question that the satellite it's very difficult to pass the same position, the same locations, the same orbit. It's very difficult. But of course, it's difficult. But if it's small, if the orbit is not perpendicular baseline is not very large, we can use the mathematical method to remove that. The orbit effect and the topographic effect, actually, we can remove by our model, by calculation. So just think that simply this passes through the same area and acquired the second image by the blue wave. You can see the blue wave touch the blue surface and come back. So you know, for the volcano, the center of the volcano, normally the subsidence rate or subsidence amount is larger. And for the far field, of course, there's no subsidence. For the far field area, we think that there's no subsidence. So the phase difference. So for the far field area, because there's no subsidence, so we consider the red and the blue waves, the phase change for this area is 0. And toward the volcano center, the subsidence amount is larger and larger. You can see the wave of the blue wave has a longer and a longer travel. And for because the signal back to the radar received by the satellite radar is go and return, so it's 2 times go and the return signal, go and come back. So we can see only the half wavelength of subsidence for the satellite itself. It receives the 1 wavelength of difference. So the subsidence of half wavelength, and for the radar receiver, it will receive the wavelength difference. So means that 2 pi of phase difference. 2 pi of phase difference. You can see here to here subsidence. Here you have a subsidence of half wavelength, but the phase change from here to here is already 2 pi, already 1 wavelength of difference, and 1 more 2 pi. 1 more 2 pi. So you have 2 pi, 2 pi, and 2 pi. 3 fringes from the surrounding area to the center of the volcano. And you know that each circle of fringe corresponds to 2 pi. And each circle of fringe corresponds to half wavelength of subsidence. So from here to here, from the surrounding area to the volcano center, we can see half wavelength of subsidence, half wavelength of subsidence, and 1 more. So here, because we use the ERS-1 satellites, and the wavelength of the radar panel or radar payload is 5.6 centimeter. So here in this figure, we call it as an interferogram. Each circle of fringe corresponds to 2.8 centimeters of subsidence. So just after the eruption and during 1 year, the volcano has a continuous subsidence, but it's a very high mountain, it's a very hot mountain, it's very far away from Taiwan. For us, it's almost difficult to go there for 1 year measurement. But we use just the 2 images, one acquired just after the eruption, and the one other 1 year later, acquired 1 year later, and use these 2 images, we can generate a map of subsidence. From this interferogram, you can see 2.8, 5.6, and then 8.4 centimeter. So we know that during this 1 year later, comparing with the surrounding area, the volcano center is 8.4 centimeter of subsidence. So this, you can see this technique is quite powerful. In the 1993, we successful carry out this kind of calculation. Of course, right now we have well developed many new technique that's more advanced and more powerful than this one. But the basic idea is always the same. We can use 2 images and to know the deformation. Of course, the volcano subsidence is easy to be observed, but much more important cases is from the earthquake. Okay. As I mentioned to you that the first image, the interferogram, is generated and published by the French people named Massonet. Here, I didn't put here. Okay, I don't remember. No, not here. The author of this paper is Massonet. They use 2 images, one before and one after the Landers earthquake. The Landers earthquake occurred in 1992, the June 28. And the satellite, actually the Landsat EIS-1, launched just before this earthquake, and then already acquired some image of different area, including this area. And the earthquake, that is a huge earthquake, occurred, and then Massonet, they acquired, and their team acquired the second image after the earthquake, and they compare this image with the archive image before the earthquake, and then they generate this figure, published in the submitted to the Nature, and be accepted and published very, very soon, because this is, we can consider as the first image of the earthquake. In this image, you can see the fringe. You know right now very well that each circle of fringe corresponds to 2.8 of centimeter of deformation. Maybe uplift, maybe subsidence. It depends on the fringe toward which direction. Okay. And here you can see the black line shows the fault line. Actually, the surface rupture associated with the earthquake, and surrounding the surface rupture, you can see a very beautiful fringe cut by the black line. Means that the fault moved along, the surface moved along this fault, and on both sides you have the corresponding deformation. Of course, the largest displacement occur along the fault line, and to the surrounding sides, smaller and smaller, something like that. So this is we can say that by using the satellite, we can measure the deformation. We can have not only the image of the damage image, but we can have we can calculate the surface deformation directly by using the satellite image. But keep in mind, one thing important is that this kind of image, this kind of deformation, this kind of measurement is a relative measurement. It's a relative data. If you want to compare with the GMASS, if you want to compare with leveling data, you have to put some control point and try to tune your result with that. So this is relative. It's very useful, but if you want to do more calculation, more detailed study, always it's better that to compare with some local measurement and in situ measurement. That is the important idea. So here you can see because they are French people, so they published this paper and very happy, and because this image has been, this paper has been accepted and published very quickly, and also this image has been used as the cover page of this issue of Nature. So you can see some French here. I will read that. because I got my PhD in France and I worked in France for a long time, so maybe my French is better than English. So I try to explain you this image by using French. It's an image d'un tremblement de terre. Tremblement de terre means earthquake. Okay. The Permian image interferometric. You know the interferometric. Okay. So interferometric is interferometric. Un tremblement de terre is earthquake. Obtenu par CNES. CNES is a French space agency, but right now the satellites are more, they don't launch the many satellites by themselves. They acquire the Airbus and the other company, the private company, to do this kind of work. So if you want to use the image, satellite image, right now we don't contact. You don't need to contact the CNES directly. À partir de image radar acquis le satellite européen ES1. So you can see this ES1 satellite. They use that to do this. So avant et après le 16 longest magnitude 7,3. So it means that they use two images before and after the earthquake to generate this result. So of course this is the first one, the important one, and after that we create not crazy. We use we has been largely applied for many cases. And when I was students in France, so of course I use this technique with my colleagues and try to study the deformation of Taiwan. This is the uplift of Tainan, the southern Taiwan. Is actually the Cheng University is located in this city. So the uplift of the Tainan tableland, and this has been published in 2001. I don't want to talk much about the detail. Let's see some application of the InSAR in Taiwan. I just show you 2 or 3 cases, and then I will talk you about another new technique. So this technique, I mean the InSAR technique, has been largely applied, as I mentioned, and not only in Taiwan, and we also apply that in many different cases in different countries, including the Himalaya, Tibet, and some active deformation, deformed area. And this case is a very early case. I published this result in 2004. This is from Pingtung, okay, in southern tip of Taiwan. And this area, I would say the coastal plain, it's largely covered by the fish pond. Means that the aquaculture in this area is very important economic activity. So for this kind of fish pond, the people pumped a considerable amount of groundwater during the winter, and for the summer, because the precipitation is enough and the temperature is higher, so they don't pump the groundwater. But during the winter, it's dry season, and also the surface water is too cold for the fish and the shrimp for their aquaculture. So they pumped the warmer groundwater for their fish pond. So you'll see the seasonal difference of the length of subsidence in this area. I'll show you one. This is the first test. I just use 5 images acquired during the spring from the January to the May of the 1996 of this area. So you can see 4 interferogram. And the first one, I used 2 images. I used the mass image of January and slab, the second image of February. So, and this one is January with March, January with April, and this one is the results between January and May. So all of 1996. So we can consider these four interferogram for the time interval of 1 month, 2 months, 3 months, and 4 months. And you can see for this one, we don't see any fringe, and here a fringe, clear fringe, and the 2 fringe in the southern part. And the photo I show you is from here, from the P point P. So you can see the land subsidence occurred during 5 years. Excuse me, 5 months from the January to the May, and it's a continuous subsidence by using the two fringe. You can measure that. You can estimate that by using the fringe here. And as I mentioned before, each circle of fringe corresponds to 2.8 of centimeter, and here 2 fringes, it means that 5.65, more than 5 centimeter of subsidence occurred only during 5 months. So means that in this year, only during 5 months, you have a subsidence of 5 centimeters. That is very, very rapid. Actually, it's unbelievable. But fortunately, right now, this subsidence is ceased because the government already pay attention to this area, and the local people knows that they cannot continue to pump the groundwater by this way. So right now, the subsidence was ceased. But before, in that more than around the 25 years ago, we can see the subsidence of this area is quite fast. So every time during that period, after every typhoon, this area is always flooded by the not only water but also flooded by the mud. This is a photo I took from this area. So wait a minute. So we want to know more details. We want to know if this subsidence is really caused by the water pumping. So I will show you this result. This figure shows you the daily rainfall from the 1996 to 1999. You can see here, this is wet season from the April to the October. This is wet season of this area, and this is dry season. Okay, from October to the April of next year is dry season, and the wet season and dry season like this way. So it means that during the winter, the precipitation is very, very less in the southern Taiwan. Okay, even less than 10% of the annual amount. But in the summer, during the summer, the precipitation occupied more than 90% of the annual amount. So, and also, as I mentioned, the winter, because it's very cold and it's very dry. So let's see what's the difference. I using the image pair. Here I'll show you this pair for the dry season, the W1 for the wet season, D for the dry season, W for the wet season, and dry season. So I totally use the 6 image pair, 3 for the dry season and 3 for the wet season. And let's see the difference. You will see that very clear. For these 3, from dry season, you can see very clear fringe in this area. The P always show you the fish pond area, the photo area, okay. So it's the subsidence center of all these fringe, okay. But for the wet season, it's very mess. Actually, this is not, you cannot see the clear fringe here. So we can say that the subsidence occurred in the dry season. And then we can compare this result with the groundwater level. So here the black dot in the map shows the location of the wells. And I just show you 7 wells on your right-hand side. And the red line here shows the fluctuation of the groundwater level. You can see it's clearly the, how to say, the seasonal pattern. In the winter, you can see the red line here, the water level of the groundwater level, subsidence, and during the wet season, I mean the summer, is come back and decide going down and come back, go down and come back. So you can see the very clear the seasonal pattern, and also our interferometric image pair here. I will show you. I show here the dry season, wet season, dry season, wet season, and wet season and dry season. It corresponds to these 6 image pair. So we can find out during the dry season, I mean the winter, the water level, the groundwater level is lower because it's descending because of water pumping is lower, and the land surface we can observe the slightly subsidence. But during the wet season, the water level, the groundwater level, come back, it's uplifted. But the land surface, because the buoyant support has been removed, the water support has been removed. So even the groundwater level is higher, come back, but the land surface cannot come back to the original level. Maybe there's very slight uplift, but it's not enough. So next the dry season come back, the groundwater level is because of water pumping, so it's lower, and the subsidence occurred on the land surface. And then during the dry in the coming wet season, the groundwater come back, but the land surface cannot come back. So we can see the land surface subsidence of this area. We can see the seasonal pattern is caused by the water pumping, but it will can how to say the groundwater is descending, but the land surface will has some subsidence, but during the wet season it cannot come back. So it's not like the groundwater. It's you can come back and with a seasonal season, but a seasonal pattern. But the land surface is a one-way deformation, always subsident without the coming uplift. So the subsidence accumulate in this area. So and finally is make this area because of water pumping is lower than surrounding area, and then very easy, is always threatened by the flood and or inundation during the, how to say, typhoon season. So it's a human activity. Its subsidence is caused by the human's activity, and then I will show you a case from the tectonic activity. I mean, it's caused by an earthquake in Taiwan. It's a 1999 Chih-Heng earthquake, and this result I also published in 2004. And you can see the surface rupture of the associated with the earthquake. Very huge offset here, and this the hanging wall side of this fault has an uplift of almost 2 meters high. It's 180 centimeters of uplift of the eastern side, I mean the hanging wall side. So we have many measurements along the fault line, but for the surface, the largely surface deformation, because we don't have a detailed measurement of this area before the earthquake. So it's very difficult to calculate the deformation field of this area. We can measure only deformation, or we can say the displacement along the fault line. But for the large deformation field, it's very difficult to measure that. So, of course, we can use the InSAR technique to calculate that. Here, I show you the image pair that I used. It's all acquired in 1999. The red star here shows the earthquake. Okay, so I use 1, 2, 3, 4, totally 4 images. 2 acquired before the satellite, before the earthquake, and 2 after the earthquake. I mean the main shock, and to generate 4 image pair. For A, the interferogram A, I use 2 images all acquired before the earthquake, and the B and C, I use all the image 1 before and 1 after, 1 before and 1 after, but of course different time, okay, different timing for the B and C, but it all includes the earthquake event, and the D, the 2 images are all after the earthquake event. So you can see in the A and D before and 2 images after, you cannot see a clear fringes, and however in the B and C you can see the earthquake pattern, I mean the deformation pattern clearly shown in the football area, I mean the west of the Chung fault, the main surface rupture of the earthquake. So you know very well that each circle fringe corresponds to 2.8 centimeters, so we can calculate the deformation field of this area. And here is a coastal plain, so this is a metropolitan area, and all damage actually focus in this area. So that's this data, this deformation field actually is a very important result. And later I will come back to this result. Let's see, continue. So you know the fringe here corresponds to the deformation, so we can use that to calculate the deformation field as shown by the figure in the right-hand side. The principle is like this one. This corresponds to the 2.8 centimeters, so we can continue this technique we call the unwrapping, and to calculate the deformation field from the upper figure shows the ramped result, means the interferogram, and the lower figure shows you the unwrapping result, means the deformation field. So the upper figure is the left-hand side, and the lower figure is the right-hand side. Okay, so we can compare the underground structure and to discuss the possible mechanism for this deformation. So I don't want to talk too much the detail of this study, but let's come back to this figure. You will see that even this result, we think that is good. This result is quite good for the to construct the deformation field. But you can see right-hand side here, and the east to the Chung fault for the mountainous area, the result is not good. There are several reasons. The first one is that this is a mountainous area, so the topography is complicated. Topography is much more complicated than the coastal plain. The second reason is that this mountainous area is covered by the vegetation, so the coherence of 2 images will be too low because the tree and the vegetation will change along with time. So you cannot compare the pixel by pixel. And of course, there are some other reasons. For example, you don't have, I would say, the building, you don't have the infrastructure to compare the images, the deformation rate or deformation amount is too large and will make the coherence too low and blah, 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 blah. But the two most reason is that the mountainous area with the vegetation make the coherence too low. So we cannot calculate the interferogram. We cannot calculate the fringe, the phase difference of this area. So in order to overcome this technique, we have to develop some other technique. So here shows you the interferogram, including of course, the information, I mean the displacement, but also orbit effect. We can remove that by the calculation. And also some atmospheric effect and also some noise. Okay, so they correlate the result. So we have to remove all this effect to obtain the real deformation information. So we apply a new technique called named persistent scheduler. For this kind of technique, we use not only two images. We use not only image pairs. We use a series, but we use a series image, at least 15 images, sometimes more than that. More image, more is better, okay? We use a series of images of the same area, and we don't calculate the phase difference directly between these two images, but we choose the stable pixel in this series of images. This pixel can be, for example, the large tree trunk, or electric tower in the mountainous area, or isolated building, houses, or big rock in the mountain. We choose this kind of stable pixels, and then we calculate the phase information, the phase change of these stable pixels along with time. So this is different to the InSAR. InSAR, we compare two images and to compare the phase difference of all pixels directly. But here we just choose the stable pixel and compare the phase change of the one pixel to itself along with time, So this kind of technique we call the persistent scheduler. I know the time is limited, so I don't want to talk too much about the details. You just know that InSAR technique is very powerful, very useful. And for the earthquake event, for the rapid event, for the hazard event, it's very useful till now. But if you want to see the long-term deformation, sometimes it's not very, very good because the coherence will be too low. Okay, and especially for the mountainous area or for the long-term deformation, it's not very useful. It's not very good. So PS InSAR is a new technique developed to overcome this problem. And there are also some, for example, small baseline, STM, InSAR, and so many different InSAR. You can see the title, before the InSAR, we add always some later. That means that's a new technique for InSAR. Okay, so the PS InSAR is right now is a well-developed one. So I just show you. I think I have no time to show you these two. I just show you one, only the one result by using the PS InSAR result. So it's from the central Taiwan here. Okay, you can see a river here. This is largest river in Taiwan. We call it the Zhuoshui River. So here we have also the problem of water pumping, not only because of aquaculture, but also from the agriculture, because this is our most important productive area of Taiwanese rice. Okay, so let's see the result from here. You can see the result, the color of each pixel shows the deformation amount. No, rate here is a year, millimeter per year. So you can see the red color represents a higher subsidence rate, and the green color close the mountain close to the mountain edge area. There are no subsidence, but only in the coastal plain, and here coastal plain you have a 2 subsidence center. And dashed line here shows a Taiwan high-speed rail, and this Taiwan high-speed rail just passed through the rapid subsidence center area here. So how can I say, the continuous observation is very, very important for this area. And the result you can see is a pixel by pixel. So along the road and the building area, city area, rural area, and also close the river, you can see some bridges. We have always a result, a beautiful result here. Here you can see very strange pattern subsidence here. That is industry park, industry area. We call the Zhangbin Industry Park here. So normally we cannot go to the area because it's not open for public, but we can still measure the deformation of this area by using the remote sensing technique. Okay, so we can see the continuous subsidence over here, and we can compare this result. This is our result with labeling and the GMSS data. So this is a subsidence center from our by using the series satellite images, and this is measuring result on the in situ. I mean from the land surface by labeling and the GPS. So it's quite similar, but our data you still can see some very beautiful pattern. For example, in the industry park area, we still have a very beautiful result. And finally, I will show you the last slide, and I will stop here. It's that, of course, the subsidence of this area is it's very large, and our government, of course, pay a lot of attention to this area. So they built a network of observing wells in this area to observe the groundwater and try to know the subsidence, because our former previous case from the southern Taiwan, you know that the subsidence always has a very close relationship between the water pumping. So they want to know the relationship with the water pumping. So they built a network, the well network, to observe that. And we have our surface result, surface subsidence result, and we can compare that with groundwater leveling results. And one thing very, very important, interesting is that you can see this line is from a well, and this is the result from the welling data. I mean, this is a real groundwater level data result. So you can see the subsidence along with time. The water head, I mean, the level is lower and lower. But for the surface of observation, for the same location, you can see is this line. This is from our surface measure result, from the level result, and also from our satellite interferometric, the PS result. The subsidence rate is much rapid than the subsidence of the groundwater level. So it means that if there are some subsidence not caused by the water pumping, even there's no water pumping, maybe you still have this subsidence. We can say the upper part, this subsidence caused by the water pumping, but lower part, the subsidence may be not caused by the water pumping. There are some mechanisms to generate this subsidence. So I have to stop here. I know the time is up. So following before I prepare another case, but I think I don't have time to talk about this case. But I will give this PowerPoint to TSU. So if you want to have this PowerPoint, you can download that directly from their website. So I just stop here. Thank you for your attention. Thank you. Maybe we can do that. If anyone have a further question or any idea or want to know more something about the SAR technique, you can write to GSU or by the Facebook or send your question to them directly, and then you can forward that to me. If I have time, I will answer you by email. Okay.
Okay. Thank you.
I'm really sorry that because I know that for me the time is up. I have to leave.
Okay. Thank you, Professor Chang.
Thank you.
And we have a question. Let's close. We have 2 questions. And please write down your answers on this phone as a proof of attention. And if you have any question, you can also write down in this Google form.